All right. So, hold on. Got a bunch of people in here again. So, exam 2. Oh, lost my pencil. So, I just wanted to start by saying the 3 most important pieces of information are going to be like kind of these 3 sheets. So, this one was one. Like Eden was kind enough to photocopy for me, but Shannon had it on the board the other day. It's each, let me go to like yellow. Each symbol, what they mean, and then the units for that symbol. So knowing this, all these, is going to be super important. And we'll kind of go through some of them more later on. I know a lot of you probably have this already. If not, maybe it'd be a good idea to like watch the YouTube video after and then write all these down so you have them for the test. Um, this is the other piece of really important information. It has basically everything you need to figure out either ohms, volts, watts, or amps. So amps is current. R means resistance. V is volts, obviously, and then P is power, or joules. That'd be the unit from over here. Power watts. So those two, and then this is kind of the cheat sheet that kind of goes with this unit, and it goes over everything that we went over in the last during this unit, and it has everything kind of laid out nice and neatly. So it's super, super valuable. It's the front and the back. I think I took a picture of the front, but it has stuff in the back, I'm pretty sure too. Let me double check. Yeah, but it's mainly that front page. So this says everything about the parallel plate capacitors, electrostatics. It gives you how many electrons are in 1 coulomb and vice versa. This is going to be really important. We'll go over all this stuff kind of briefly, and then I was planning on going over all those short answer questions. So, I guess just to start, the exam is going to be 30 multiple choice questions. So very similar format to last time. Except 5 of 7 short answer this time. And we were given all 7, so I'll kind of go through those later like I already mentioned. So starting off, I'm going to kind of go through the study guide and hit all the points. I'll try to hit all the points that she mentions on there. And then if we have questions kind of along the line, feel free to ask. If not, we can leave time for some questions and conversations at the end. So starting off, I wanted to talk about the law of conservation. So basically, it's just saying that charge cannot be created or destroyed. And so that's where we're able to get a lot of these kind of equations and stuff from, is that idea. It's a very important idea in electricity. So when something has, so let's go, protons are positively charged. So if something has a lot of protons, or excess of protons, it's going to be positively charged. And electrons are negatively charged. So something with a ton of electrons is going to have a negative charge. So kind of an example of that maybe there being a question. If she asks a glass rod is charged to, let's say, plus 5.0 nanocoulombs. Does it have an excess amount of electrons or protons? And can we figure out how many? Right? So I think that was actually a homework problem, maybe on like the first section. So if you want to kind of follow along, I think I can double check. Yes, that's week 8 homework, basically. No, I'm sorry. One before that? Yeah, week 7. So they ask, a glass rod is charged to plus 5.0 nanocoulombs by rubbing. Have electrons been removed from the rod or protons been added to the rod? So we know there's another important piece of information. Protons don't move. Only electrons move. So if there's a positive charge, that means it's just lost its electrons, which makes it positive because there's more protons than electrons. If it's perfectly balanced, then it won't have any charge. And then obviously if it's got a bunch of extra electrons, that's what makes it negatively charged. So I think what I wanted to go over next, the basic equation, right? It's almost like it's a conversion. So that's on that cheat sheet up here. So we can figure out, okay, it's nanocoulombs, nanos, 10 to the 9th. We can convert the charge in nanocoulombs to exactly how many electrons were transferred. So yeah, that's question number 1 basically in week 7. And there's another important piece of information on this sheet I kind of want to talk about. And I know there's a short answer question that has to do with it. It's conduction, and induction. So the way I like to think about it, and I think Shannon does too, is conduction, you need to be touching it. So you're either taking electrons or giving electrons, depending on the charge of whatever you're touching with. So we'll write that down. Conduction by touching. Induction is without touching, and you need a ground. So kind of the process is you say I'm negatively charged and somebody puts a positively charged rod near me, right? My electrons are going to go up trying to get to that positively charged rod, but they're not going to be able to make it because we're not touching. But if I'm grounded, we can pass those excess electrons will pass through the ground, right? And then say a bunch go out to the point where there's more protons left over than electrons, and you take that rod away, I will now be positively charged, right? So that's kind of how induction works. So induction is without touching and with ground. And then I wanted to talk a little bit about conductors. So conductors are things like metals, like copper is a very commonly used conductor. Basically, conductors conduct electricity, or in other words, electric charge easily passes through them. as well as spreads evenly. So when we talk about plate capacitors, that whole plate is getting the same amount of charge because it spreads evenly across the plate, because it's a conductor. Insulators, on the other hand, are kind of the opposite. They don't conduct electricity. So it could be things like plastics and rubbers, or like ceramics, materials that, you kind of think of. The thing I like to think of is, if you're wearing, people always say if you're wearing rubber soles and you get hit by lightning, it'll save you from the lightning strike, right? So that's because rubber is an insulator, and so it won't be a complete circuit, and the electricity won't be able to pass fully through you, I think is the idea. So we talked about induction, conduction, conductors, insulators. Okay, so now I kind of wanted to get to a big part. Coulomb's law. Excuse me. So that's this equation. I think we worked with it quite a bit in some of our homework assignments. K equals Q1 times Q2 over R squared. So force is what we're going to be solving for. The units are coulombs. I know Jeremiah was kind of asking about this. Coulombs are amperes times seconds, from what I understood. I kind of did some research on that. What is a coulomb? Coulombs is literally 6.24 times 10 to the 18th electrons. Because if we're going to talk about current in a little bit, current is the flow of electrons. So if you want to measure how much current you're getting, the first guy to figure that out was a guy named Coulomb, and he named it after himself. And they ultimately figured out, like, okay, 1 coulomb is this many electrons, from what I understand. Another piece of information that we're going to need is K. So K is the dielectric constant. Oh, it's just a constant. I'll call it that for now, because I don't think technically the dielectric constant's a little different. I think is that E? Epsilon? We'll get there. I have it in my notes. I'm sorry. Okay. So K, especially when you're using Coulomb's law, is a constant, and it's 9.0 times 10 to the 9th. And so that's something we're definitely going to want to have written down. I know it's probably on this sheet. I'm surprised I don't see it. She gives us the permittivity constant. That's epsilon.
It's in the middle on the top.
You see it?
Yeah.
Oh, right here. Good stuff. And she gives the other equations here too. So this is a good section. So, okay. That's a good one to remember. Now you kind of know where it's written down in our notes. And another thing I wanted to mention is there's a couple problems where we needed to use this kind of equation. So if we're given a mass and acceleration, that's another way that we can find force. So maybe, for example, she's asking for a current or something, and we're given a mass and acceleration, we might have to kind of work backwards. Hope she wouldn't make it quite that hard, but I think it did come up in our homework, so I just wanted to mention that. And I'm pretty sure R is the radius, right, Jeremiah? I don't have that written down.
Yeah, it's the radius, absolutely.
Cool. So R is the radius. So I think we, if I can look back, we had to use that on week 8 or maybe end of 7. There was a few problems where we needed to use that equation. And then this is, yeah, it was week 7. And we kind of get into having to draw the directions of the currents. So kind of like those problems where we had the plus and maybe a negative, and you had a certain amount of charge in coulombs up here, and you had to figure out how much it was going to push, and we had to use this equation. So maybe toward the end, if people want, I can try to go one over those.
The R does not always seem to be a radius. Sometimes it is just the distance in between the particles. There's a practice problem where it just says two particles 2 centimeters apart, and the radius or the R is just the 2 centimeters.
Okay. So we could maybe indicate that. Can be just the distance. Do we kind of all agree on that? I think that makes sense to me, especially when we're doing these ones. They definitely gave us like stuff like that, and we had to figure out. I guess there were some where we needed to trig and stuff like that. Um, but honestly, I can't see her giving us the super hard ones. Like I said, if we want to go over those ones more, I kind of just want to get through everything, and then if people have questions and stuff, we can go over stuff. Like, if people want to see problems, we can kind of do that toward the end. Okay, and then there's one last thing I kind of wanted to say when I was talking about Coulomb's law is field strength. So field strength is indicated by the letter E, and there's a few equations that have to do with that. So one was the field strength equals force over charge, and the other one was K times uppercase Q, which in my notes I have is just source charge. So I'm not exactly sure what the difference between like a lowercase q and an uppercase q is, because to me it seems like they're kind of interchangeable. Does anybody else know if there's a difference between the two?
I don't think there's a difference because I think we talked about it with Tim in the tutoring lab. I don't think so.
Okay. Yeah, it didn't seem like it to me either.
Yeah, because even like looking at the study guide that she gave us, like our cheat sheet, she kind of like interchanges the Q throughout too. Some of them it's uppercase and some of them are lowercase.
That's a little confusing.
Yeah.
But basically, no, it's the charge. Q, if you think Q, think charge. Basically, right?
I think the uppercase Q is when there's a second charge in the problem.
And then that would be like the first charge, kind of like, or like the source charge.
Yeah, so you'd use like whatever the first charge is as Q1, and then whatever the second charge is as the uppercase Q.
That would make sense too. Maybe we didn't have many problems where it had more than one. So we'll say uppercase Q, source charge, lowercase q, secondary charge. And then maybe we'll indicate can sometimes be used interchangeably. It seems. Maybe we'll have to ask Shannon for some clarification on that maybe before the test.
There's a practice problem where they use that, where the particles themselves have a plus 10 nanocoulomb charge, and then the thing in the middle has a 1 nanocoulomb charge. So I think she's right. When you start having more than one charge in the problem, you use the first one, like the thing that isn't moving, as the big Q, and the thing that is moving as the little Q. As far as this problem goes, that makes the most sense.
Okay, can you
It's
just
on
say that
page-
again? I'm sorry.
So on page 78, there's a practice
Mhm.
problem that basically two like dots are sitting there, and then a dot is put in the middle. So for
Okay.
that case, the two dots on the side, the one that is not moving is the big Q, and the dot dropped in the middle that is being pushed around is the little Q. So it seems like the thing that is unmovable, the thing that's doing the moving is the big Q, and the thing that is actually being moved is the little Q.
Okay, so we can maybe say the thing being moved. And so then that would make sense that the uppercase Q is like the source charge then, right?
Yeah, that sounds good. Yeah.
Okay. So hopefully that clears that up a little bit. I think it makes a little bit more sense to me. Well, cool. I think that covers most of the things in Competency 6. So the next thing I want to talk about. Okay. So whenever you see potential, or the electric potential, something potential, that's always going to be volts or voltage. Those kind of terms are used interchangeably, it seems like. Voltage is the potential to do work. So it's the potential to like make power, kind of. So I think that's why they're used interchangeably, because voltage is potential, like potential energy, kind of. I kind of covered this earlier, but it's important to know 1 coulomb is 6.24 times 10 to the 18th electrons. If you see this E minus, that's electrons. And then I also want to talk about, so if voltage is potential energy, source or current or charge, I mean, is kind of like kinetic energy. So there's an equation that we can use if she gives us kind of kinetic potential energy problems. This kinetic energy final minus kinetic energy initial is equal to negative charge times the voltage final minus voltage initial. I think there might have been 1 or 2 homework problems that we kind of needed that. But it's basically saying that energy is always conserved. And so these values are going to be equal, because this is kind of, because like potential always gets converted back to kinetic and vice versa. So I think that's kind of more physics 1's concepts. So I also wanted to say the sign of Q matters, right? So a positive charge is Q, is going to speed up towards a lower potential or a lower voltage. And it's also going to slow down when going towards a higher potential. when a negative charge is kind of the opposite, right? It's it's going to slow down towards higher potential, and it's going to speed up towards lower potential. Right, so I think there was a couple like concept problems where we needed to know that, and know that if you see like what a negative Q means, it's kind of like the opposite, if that makes sense. So like if you had to use this equation, you'd have a double negative, right? And so to cancel out this one. So if you're plugging in math problems and stuff, always be sure to remember that this Q is negative in the equation, because I think that could be easy to kind of screw up. Okay. I also saw and wanted to mention, if you see electron volts, it's the same as coulombs. So coulombs kind of has a similar equation to our Ohm's law equation, but to find energy, right? So we go back up here. U, does she have U on here? Yes. It's kind of the same thing as work. It's in joules. So energy, right? If you see energy or work, it's going to be the same thing as U. So this equation looks really similar to the Coulomb's law equation. Sorry if I said Ohm's law before, I meant Coulomb's law. But it's with U, so it's U equals K times Q1, Q2 over R. So we might have some equations. I think it's the same constant of 9 times 10 to the 9th. And this is going to be a radius or distance. And these are going to be two different charges again. So we might have to use that one. I also wanted to mention, so what are coulombs? Coulombs is like, what did we say earlier? Charge. So Q is your charge. This is where it gets a little tricky, right? So you're gonna see C, and you're gonna you're gonna think it's coulomb, so this is charge. If you see, sometimes you see another C in equation, capital C, but it means capacitance. So you just kind of have to think about the question and make sure you're using the right equation for the right stuff and the right C for the right thing, right? Because now I was going to talk about capacitance. So let's go down here. Make sure I'm spelling it right. I-10. So, like I said, it can be shown as the letter C. And basically, it's the charge divided by voltage. This is the best way to define capacitance for most problems. And then the units will be farads. So farads are really, really big, right? So usually you can expect if you're going to get an answer for a capacitance question in farads, a lot of time it's going to be a very small number, like microfarads or millifarads or nanofarads, right? So if you're doing a problem and you get a number really big, like, like let's say like 20 some farads, I would venture to guess that you might have made a math mistake along the line, because I think for the most part we can kind of expect really small numbers with farads. Who knows, maybe she throws a curveball, but I think if we're thinking practically, usually it's very small, right? It can also be, another equation is, I'll get rid of that, C, for capacitance, equals epsilon times, I think A is area in this case, over distance. No, I think it is. Jeremiah, can you confirm whether that's area in that equation?
I'm pretty sure, because normally this has to do with the discs, so you're looking
Yeah.
for the area of each disc.
Yep.
Pretty sure.
Okay.
Let me check though.
That's what I had in my notes, and I think,
Yeah. If you look at, it'd be on page 89 or 90. You're right. It would be area.
okay, cool. I just wanted to be sure.
Yeah, for sure.
Nice. So, oops, I forgot the K. K times epsilon times area over distance. I guess there would be some cases where you wouldn't need the K, which I was, but for that, you probably just would use, this one, right? So this is where the K gets a little bit different. Um, you might have to look at your, there's on page 91, and while we're over there, there's a little box kind of on the right here. Is the dielectric constants, and it gives values for all these different materials. So you might have to look at like what material you're using if we have an equation where you're going to need to use this, because your K values can be different. But there is one constant, epsilon is the permittivity constant, and it's always going to be 8.85. Yeah, 8.85 times 10 to the minus 12. And then that would be Coulomb squared over meter squared. But that doesn't really matter that much. Normally you're just going to plug in this number into the equation. And capacitance is in farads, so you don't have to worry too much about the units canceling out. But yeah, so like I was saying, if a material is a dielectric, you need to know its constant. So page 91. And then I just wanted to go over, maybe define what dielectric strength is. So it's the maximum field strength that a capacitor can hold before it sparks and pops. So the max field strength the capacitor can hold. And so we kind of learned about how capacitors work, right? They store charge, and they kind of almost convert that electrical energy into like potential energy, sort of, and store it and then convert it back, I think. Because that's kind of how batteries work, right? We'll get more into how batteries work later on. I took notes on that. So ultimately, we can kind of combine all those equations that we were talking about. So and maybe mix some things around. And I think this is coming from the next page, 92. The U equals the charge squared over 2 times the capacitance, which also equals 1/2 times the source charge times voltage which also equals 1/2 times the capacitance times voltage squared. And you may notice I'm kind of leaving out the change in voltage. And Jeremiah kind of explained this to me. It's always going to be a change in voltage, right? You're never going to be able to just measure voltage from one spot. It's always going to be from two different parts of the circuit, right? So it's always going to be a change in voltage. So you can kind of use them interchangeably, right? So I think that covers most of the things from competency 7. Let me look. So we should be able to calculate capacitance. We applied the law of conservation of energy. Yep. Talked about dielectric materials. Described its effect on different materials. So different dielectric constants, how can they affect the field, right? So if you think about it, let me go back. If we look at this equation, the dielectric constant is this K. If something has, like in a vacuum, it's 1, right? You can see how maybe the capacitance would be, let me think about this, lower, where if you had something like strontium titanite, which is like 300, it's going to make that ratio higher. So then the capacitance will go up. Is that right, Jeremiah?
Yes, that is 100% right.
Cool. So yeah, that's kind of the effect of the different dielectrics, is how much capacitance will a capacitor have depending on, what's inside of it, or what the constant is, what the material is made out of, right? So okay, competency 8, kind of we start getting into Ohm's law. So I wanted to just talk about, I think Shannon's kind of talked about it several times, but just wanted to go over it. The scientifically, right? Current is a flow of electrons, so we can get that down. That's a good definition for now. So what actually happens is electrons are negatively charged, right? And they come out of, let's say if you have a battery has a positive end and a negative end. Electrons in reality are coming out of the negative end and flowing towards the positive. The people who were figuring this out didn't really know exactly how it worked yet before they started deciding on which way current flows, and they said it flows from positive to negative, right? It doesn't affect the math at all. It's the same thing, just backwards. And so that's kind of how it still is. It's still how we think about it. So for our purposes, always think about it. So flows from the positive to the negative. But you need to, I think it's in the study guide that you need to know that that's not actually true. That's just how we think about it, right? So okay, current is the flow of electrons, or you could say the flow of charges, right? Charge is indicated by Q, right? Q. So current basically is how much Q we have over a certain amount of time. So, and then I is the kind of symbol we use for current. So that's one equation that we can get. If we're given a charge and a time, we should be able to find the current from that. I wanted to talk to you about resistivity. These were kind of where it was a little tricky for me personally. There's a difference between resistivity and resistance. Oops. So resistivity is denoted by the symbol like this. It's called rho. I don't know exactly how to. I think that's a guess. It's this symbol, right? The kind of squiggly P. And it basically means ohms times meters. So if it says in a problem, the resistivity is something, it's not the resistance, it's the resistivity, right? And there's a few equations that we use this for. Let's get down resistance first. Resistance, we use the letter R, right? And the units for that are ohms. So it's this little symbol for ohms. So if you're trying to calculate resistance and you're given a resistivity, you can use this kind of equation. So it's that rho times the length over the area. So I think we had a couple homework problems like that if you go back through where it said the length of a wire and the diameter of a wire and the resistivity, calculate the resistance, something like that. And so now we're talking about resistors. Maybe I'll talk a little bit about, and current, a little bit about Kirchhoff's junction law. So basically what that is it's saying this is the sum of, so the sum of all the current that goes into a circuit has to equal all the sum of all the current going out of a circuit. And that kind of goes back to the conservation of energy, right? So no energy is ever created or destroyed. So what goes in must come out, kind of, right? And that's where they get into these kind of situations where it's like, say this is 3 amps, this is 4 amps. Well, how much is going to come out on this side? All you really do in this case is know that they would add together. So coming out this side would be 7 amps. Where if you did it backwards, it kind of depends, right? So it's hard to judge how much current is going to come out on either side. We started getting into figuring that out more toward the end of this unit, where, like, say these had resistors, right? You could figure out, well, how much current is going to go down this line and how much is going to go down this one. But theoretically, if you just saw one like this, it's kind of tough to figure out, right? Like, I'm trying to think, we had some homework problems like that. We were probably given a resistivity, so then we were able to figure out like how much would go through, or we're given a different value later on, so you're able to figure out like how much is gonna go through, right? So in this, what I'm saying is like this could be, 5 amps and 2 amps, or it could be split the same way it was before, 3 and 4. We really don't know unless we know how resistive each side is, because the basic idea is current wants to flow where it's easiest to go, right? Like water. Water goes down the path of least resistance. You always hear that saying, right? Current does the same thing. So if it's easier for the current to get this way, it's easier for it to get this way. More is going to go this way. It's going to have a higher amperage. And if it's harder for it to go this way, it's going to have to wait till this all fills up, and then it's more worthwhile for it to try going down this side, right? So there'll be probably a couple of problems. I think page like 115. I labeled mine, but week 9 homework, there's kind of some problems that go over that. We want to look those over. And then the next important piece of information is knowing Ohm's law. So Ohm's law is basically what we've been using for like the last half of the unit. It's kind of this circle up here, right? So this is kind of the main dude, or I guess it would be this one. Either or. I'll write it down here too. So I remember it personally like V equals I times R. It's the same thing. If you divide both sides by resistance, you'd get I equals voltage over resistance. And that's kind of just the idea that you can, if you have two of these pieces of information, you can find the other one, right? And that's super important in electricity. And it's like what people get tattooed on them and stuff is that circle, or even just this equation, right? So we'll kind of maybe go into some problems. I think there's some short answers that involve that. I know that kind of week 11 stuff definitely gets into. You need to know that. But next I wanted to just kind of go over batteries. And how they work, right? So I know in the video Shannon kind of got into the chemistry of it and stuff. Batteries are actually kind of like galvanic cells, right? So, but I think the main three parts that might come up on the test and that we should focus on are knowing that there's an anode, which is the negatively charged side, a cathode, which is that positively charged side, and then an electrolyte, or in chemistry we called it like a salt bridge, right? So, kind of something, if we have a battery, there's kind of this, maybe we'll do like this, maybe like green area, say this is the cathode, this is the anode. So basically the anode and cathode can't really get to each other, right? Unless they go through this kind of bridge in the middle. And what happens is this, she goes into it a little bit more in detail, but basically there's a kind of a chemical reaction between these two sides that causes a buildup of electrons at the anode. So we'll say this is negative, this is positive for now. So a bunch of little electrons get all built up in here, right? Then you have, say, a wire that connects either side of the battery. Don't ever do this. Don't ever take a battery and put a wire on it. You'll hurt yourself. But the idea is once this charge is connected, this allows the electrons to flow through. This is from the positive side to the negative. It allows them to pull through until the chemicals fully convert to either side, right? So that's why batteries only last a certain amount of time. It's because it's actually like a chemical reaction. So what it is it converts chemically stored like potential energy into electric kinetic energy. Right? So hopefully that kind of was like a basic explanation of how a battery works, because I know she asked about that. So batteries also kind of get into the whole idea of field strength. I think we mentioned it earlier, but field strength equals velocity over length. I keep saying velocity. Voltage over length in a wire So if you're asked what is the field strength and you're given the length of a wire and how much voltage is going through, you can figure out the field strength using that equation. And then I wanted to kind of explain maybe how resistors work. So maybe I can fit it in. No. So we have resistivity we have to think about, resistance, and resistors. So resistors are actually a component in electrical circuits. We've been messing with them a bunch. How they work is they basically like kind of cause a backup, right? And they cause collisions with atoms. So all those electrons or whatever that are flowing into the resistor, they're getting backed up and hitting each other. So they're hitting together. And so what happens when stuff hits together? Friction, right? And so some of their kinetic energy, which is kind of like the current, is converted into heat and then dissipates. So then the power is decreased, right, as it goes through a resistor. So the kind of idea of dissipation basically is that converting that kinetic energy into heat, and which is dissipation. So I just wanted to go over a couple of equations that kind of have to do with that. Power equals your current times voltage, which also equals your current times resistance, which is basically the same thing as current squared times resistance, right? So those are kind of a few. I mean, I would probably use that one. But if you're not given a voltage and you're just given a current and a resistivity and you're asked, well, how much power or how much work or how many joules, then you might have to use this one, right? So let me just double check. I think that kind of goes over most of the stuff from 8. We talked about Ohm's law, we talked about batteries, we talked about calculating resistance and using Ohm's law. That circle is going to be your best friend. So like I would have like these 3 sheets at easy access when you're going to take this test. Maybe take them out of your binder and put them in front of you, especially this one, because that's kind of like the best thing, right? So then we can kind of get into the last competencies. So that's where we started talking about like series and parallel and how something's changed and the rules change when you're in the 2 different circuits, right? So let's talk about series first. So in series, we can say that current, or I, is constant throughout, or the same throughout. So we'll say the same throughout. So that means each component, if you're in series and you have a bunch of resistors, you could have infinite resistors. They're all going to have the same current, right? Because in series, the current is allowed to just pass through. And she kind of explained it like if you have one of those like windmill things in water that spin, the water doesn't go anywhere. It passes right through, but it still causes it to spin. It's kind of like that. In a series current, it's just like a thing that's there, but the water just gets right through it. And then I also wanted to say in series, resistors can just be added together. So we don't have to do any of that inverse business, which is nice. But capacitors in series, you would need to use the inverse and stuff. So what I mean by that, so say you were in series and you had like 3 capacitors. One was, they're all 10 microfarads, right? And you wanted to add them together to figure out how much total capacitance you would have. You'd have to do 1 over 10, this 1 over 10, 1 over 10. So the inverse, right? Because every number always has a 1 underneath it, technically. So if you wanted to flip those around, it would end up like this. So then you have to add all those together, right? And then flip those back around. So we'd want it like this. You know, so you'd end up getting something, in this case, it'd be like something like that. Right? So it's that whole process. So in series, so if we're in series, resistors can just be added, but capacitors, you need to do the inverse stuff. So in parallel, oh man, I screwed that up. A-L-L-E-L, yes. So we said that current was the same throughout in series. It's not in parallel, but voltage is. So voltage and those 2 pieces of information are very handy when you're trying to think about those kind of more complicated circuits and you're asked all those questions about like what's the value of each resistor and stuff. Knowing these 2 are pretty important, right? That in a parallel circuit, voltage is the same, and in a series circuit, current is the same. So if we get back into talking about resistors and capacitors, it's the opposite in a parallel circuit. So in a parallel circuit, resistors need to be added using their inverse. And capacitors can just be added together. Right? So knowing you can kind of just think about one and know the other one's going to be the opposite. So if you just remember one, you kind of can determine the other. So for me, I just think about resistors and know that in series resistors, I can just add them together, and in parallel, I'm going to have to use the inverse thing. And then I know it's kind of vice versa for the capacitors, if that makes sense. Cool. And then I just wanted to talk about multimeters. I know they weren't too bad, but I think some people don't have a ton of experience, so I just wanted to go over. So if you're measuring for resistance, oops, you need to use the little symbol that kind of looks like that, circle with an ohm sign in it. You have to set up the circuit in parallel, and the power must be off. Right, otherwise it won't work. And I can see her probably asking a question about that on the test.
Brady, I think you're mixing things up. When
no.
you're measuring a resistor, you put it in series. When you're measuring the voltage over a resistor, you have to put it in parallel.
Okay.
So when you hook up a multimeter, there's actually no power source available, and you hold the black and the white. Remember, you sort of tied it around those pins. and
Yeah.
then you just measure it like that. So that is actually in series. When it's in parallel, it's like the circuit is actually built and you're not breaking the circuit, you're just touching it. That is when it's in parallel.
Do you know where we took notes on that? I just want to make sure maybe I mixed something up. Because what you're saying makes sense, obviously. Like, I can think about, like, yeah, you're right. But I think I got that directly from somewhere in the notes.
I know there's a page, I'm not exactly sure what the number is, but it was from that video, the multimeter,
Mm-hmm.
and it had the list of all the different things for the multimeter.
Yeah.
It's
No,
page 94.
74. Yeah, we took notes on it, I was gonna say, and she like specifically talked about there was even like kind of it was like circle which one was right, and there
Yeah,
was
that's page 94 because I think it's the page right before the big circle.
94.
It has like the boxes on the side too,
Yep.
with the voltage and resistance and all that good stuff.
Mm-hmm. I see that, but that isn't what I'm talking about. There's like a
Which,
different part, like a video where she went over, she was talking, maybe even after that. Let me look.
no. See here, I can show my.
For the page 94, we had to watch a video to get those notes.
Yeah, I
Yeah.
did not watch that. So, what did they say about the resistance, series or in parallel in the circuit?
So okay, I'm
Um,
talking about it's like 130 something. It's like later on, right? And then she talks about circuits in parallel and stuff. And she's going over connecting a multimeter. And she says resistance in parallel, no power.
I have that, like, even on that video that we watched in the lab,
Mm-hmm.
because I was with like you and Grady that day. Like,
Yeah.
we have that it's in parallel.
Is it right? Okay, my bad about that. My bad.
No, you're good. No, good. That's it's lecture 10 though. And she kind of goes over that. That's where I got this information from. And then there's like these diagrams where you had to circle which one was measuring it right. Does that make sense? So you think it would be in series for resistance?
I must be thinking about it in the wrong way. If she's told us a certain way, it's got to be that way.
Okay. And I would
That's the
assume
way I look
it's
at
going to be
it.
like that on the test.
Yeah, definitely.
It is tricky.
Yeah. It's weird to think about when you're in series and when you're in parallel. It's
Yeah.
easier to see for me on the circuits than it is in real life sometimes too. But a lot of times if you have a junction, that's like kind of a good indication that you might be in parallel, right? Or you might have a possibility of something being in parallel. Because if there's no junctions, it's just going to be in series because there's nowhere where it would split it all, right? Okay. So hopefully, I think that's right. Then I wanted to talk about voltage. If we're measuring for voltage, it's going to be, we use DC current, so it's usually this symbol. And in her notes, she says also in parallel. But power on. And then the last one would be current. And you measure that. There's an A. And then this one you would have to do in series. And you have to like switch the leads. So you can say change lead. So I'll just draw that little circuit, right? So she had, maybe I'll draw, she had this guy. A. And then, I'll just do 2 of them. And then this one, shoot it like this. Go into a resistor. And then kind of just looping back around. So basically, in her example, this one wouldn't be right, because the amps in series, so we're okay there, but these volts here have to be in parallel. So this circuit looks like the right one, right? Because the amps are in series and voltage is measured on like either side of the resistor in parallel to the circuit. So
Do we
it's
need to
kinda
talk
multi-
about AC voltage at all?
I honestly really
No,
don't know the difference. Maybe
no,
Jeremiah
we
could
do
tell me.
not talk about AC voltage whatsoever in this class.
No AC?
No
Okay,
AC.
I wasn't sure because I know that's one of the short answers, so I didn't want to like leave it out if she wanted
Is it
us to
one of
talk
the
about
short
it.
answer? An AC question? Let me double. Which one is
It's
that?
like how to use your multimeter. And we have to like
Oh,
talk about how to find voltage, current, and resistance.
Yes,
yeah.
but when they
So
talk about voltage, you're always looking for DC voltage.
Okay, sounds good. Thanks.
at least in everything that we've done, it's always been DC. And I think I've asked Jeremiah about AC before, and it's a little confusing. So maybe we'll just say yeah, it's just DC. So okay, but for that short answer, I would assume it's kind of this information. And yeah, I'm on page. It'd be 130 exactly. It's right when the 12s change over to 13s. And then let me see. Uh, talk about that. And then I also wanted to talk about, this was in the study guide, an ammeter is what measures amps, which is current, right? Because if we go up here, amps is a unit. So yeah, so current. So that sheet's gonna be super handy. If you guys don't have one, maybe toward the end of the video, I'll just leave it on. Well, I suppose I'll put it on YouTube and you can kind of pause on it too. And get that down. So ammeter measures amps, and an ideal one, like in a perfect world, would have no resistance. That way you can measure the current the most accurately, right? And voltmeters, but you can guess what they measure. They measure volts. And an ideal voltmeter would have infinite resistance. As much as you could possibly have. And the idea behind that is it would draw no current. If it had infinite resistance, there'd be infinitely the opposite amount of current, and it would give the most accurate reading for voltage, right? So then, yeah, I think that's pretty much what I had for just like competencies and like what I wanted to talk about. So I guess I was gonna say, does anybody have anything, questions or anything they want to go over before we start going over the short answer questions? No? Okay. So yeah, let's start going through those ones. I bet you, it sounds like I've kind of gone over a couple of things on some of them. But maybe we can try to find problems that are similar and kind of walk through them. So, question 31. It says, induction and conduction, explain, use pictures and words, use both. So I think I kind of explained that. I talked about how conduction is when you're touching. So I guess for the pictures, there was a video we had to watch with like, it showed like kind of like something like this.
Hey
Right.
Brady,
Yes.
if you look right on like the electrical cheat sheet, that one that she gave us, she literally has the conduction and induction drawings and
Oh
then
yeah.
the words. So
There you go. So yeah, that's right on the sheet. So that should be kind of a gimme, right? Conduction is touching, and induction is not touching through ground. So you can kind of just maybe just like kind of copy your picture. And if hopefully you kind of I know I explained it earlier, so um if you don't understand, maybe you can shoot me an email or something too. But it's the idea that basically the induction not touching to conduction touching. I think that's going to be the main base of that. Okay. So we'll just say picture on cheat sheet. Cool. So 32 says find net force and direction on the point charge. So I think that kind of goes back to, I think that was our first lecture, right? We had to do that.
Yeah, the practice problems were on page 78.
Yeah. Cool. Thank you. I see that. Okay, I'm gonna go over. We'll just do 9 because on 82 because I think that's kind of a straightforward one, right? So the current looks something like the circuit. The picture that she has kind of looks something like this, right? It's a circle. Say a circle. They're both positively charged, and they both have 1 nanocoulomb. The distance halfway between is 5 centimeters. So it's 10 total. And then it says, there's kind of uncharged particle right here. And this is also a distance of 5 centimeters. So it says, what are the strength and position of the electrical field at the position indicated by the dots in the diagram below? So what's going to happen to this particle, right? Basically, these two are going to push on it. And because they have the same amount of charge, they're pushing on it with equal force, it's going to cause this particle to shoot out straight that way. Or to the right, in this case. And we can kind of do that, or figure it out by using trig. But in this case, we know that these are 90-degree angles. So that, therefore, if this is coming in perfectly, that means these are going to be 45 degrees, right? And I think we can use the idea that, well, it says, what is the strength indicated by the dot in the diagrams below? Do we need previous knowledge for this? How do we know?
you'll use like a squared plus b squared equals c squared to find the length of the side that we don't know.
Okay, yeah, that's right. So you do square root of 50, which is like 7 something. I'm sorry, I
Yeah,
did that in
it's
my head. I could walk through that.
7.07
7.07.
centimeter. Yeah.
So I just used the Pythagorean theorem quick. So both sides were 5 centimeters. So 5 squared plus 5 squared equals, we'll say, r. So this is going to be 25 plus 25. And so r is going to equal the square root of 50, which we said was, we'll say, roughly 7.07. But my question was, I'm kind of looking back on this, and I'm wondering where I got the amount of force, and if I'm wondering if I needed that from like 8 or something. Well, let's just try and solve for it. So we're looking for field strength, right? It says electrical field at the position indicated by the dot. So we went through a couple equations that had to do with field strength. Field strength is E, so maybe we can go back and see. Did I talk about E? We don't have a voltage or anything, right? I knew I talked about it up here, maybe? Yeah. So this is the equation I think we need for this one. So we have our constant, that's 9 times 10 to the 9th, our source charge, and the distance squared. So we have all those elements here. So I think I can use that one. So it's E equals distance squared, this was Q, this is K, right? So we could do E equals 9 times 10 to the 9th times, well, let's just figure out, because we'll just do this one for now, and we'll know we'll have to add them together to figure out the total amount of force that's coming out the other side with. So this is 1 nanocoulomb, which is the same thing. We have to convert it to coulombs. So a nanocoulomb is 1 times 10 to the 9th. And then our distance is the 7.07. So we'll have to do that squared, right? I think.
Also converted it to meters for this because it's centimeters.
Oh,
I
good
don't
call.
know.
Thank you,
Yeah.
Mary. So this is, it's a very good call. I would have got it wrong. Maybe I would have got partial credit. So we got to move this back 2, right? So 0.0707 meters squared. That look better?
Yeah.
Okay. So I think if we do that, what do we get? It should be, I have 1800 on mine, but now that I'm looking at it, I don't know if that's quite right. Does anybody have a calculator? I can pull mine out really fast. 1 sec.
That's what I got. I got 1800.54. And I
Yeah.
think and I think
1800.
that would be the answer for letter B.
On the same problem?
Yeah.
Oh, we're doing 9 right now. So I think what I'm doing is 1
Oh, I'm
nanocoulomb of
sorry.
charge.
Yep.
Very good. So would it just be like that? Let me get my calculator quick.
It would be, yeah, because I got 1800.54.
When you did this?
Yep. Yep.
Okay.
Yeah. And I second on that.
Cool. So we know what is the units for field strength, right? We can go back up and look at that. Otherwise, I'm pretty sure it's newtons per coulomb, right? Should not have that? Maybe we should add an E equals field strength. And it's in newtons per coulomb. Okay.
I think when you give the newtons per coulomb, you usually want to give a direction.
For sure, yeah. So what I'm doing is I've done one portion, right? So we figured out how much force this is getting pushed out here, right?
Gotcha. Okay.
Or so now we need to figure out, well, how much force is that going to cause it to go this way? And that's kind of where the trig comes in, right? So we know by kind of using geometry, if these angles are 45 degrees and these are all equal, I know my lines are a little off here, so maybe I can try to. These angles, pretend this circle's right here. These angles coming out are going to be 45 degrees as well, right? So by that logic, if we're trying to figure out, we know one side of this triangle is 1800, so we can kind of use the same thing on this triangle. This side
Hey
is,
Brady,
hi, what's up?
sorry, I don't mean to interrupt, but can you let Megan in?
Yes, I'm sorry.
Oh, it's okay. She just like tried to get in. Thank you.
Mm-hmm.
Does
So,
everyone have a unit circle so that they can identify at what angle this pressure is coming out at? The angle that Brady's talking about right now is 315 degrees, which is down and to the right.
mm-hmm.
If you don't have the unit circle, you're not going to be able to identify. I mean, I guess you could just add up the 45 and figure it out, kind of a thing. But
Can't you just do, like, say you do the cosine of 45 degrees times equals x over 1800? Though, wouldn't that work or no?
I did that, and then somehow we had to multiply it by 2, and I got the answer.
That was
I don't
my
know how.
plan, right? I think if you do it Jeremiah's way, you just get the answer right away. When that makes more sense, right? But for me, this is how I figured it out. I just did one side at a time. And then so if I do this, right, because we know one side and an angle, and so you know SOHCAHTOA. I can't see there'd be too many problems on this, and so if you're worried about the trig and stuff, just know this is like the main part of it. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over hypotenuse. So if I'm doing this triangle to figure out how much force is being pushed on the ball, I know this angle, I know this side is 1800 newtons. So I'm trying to figure out kind of this side, right? Or the x value. And then that, because that force would be, because like I said, this is the same angle here. This is the same force on this side. If we continue these triangles out, this is also going to be 1800 newtons. So we're solving for this line specifically, right? So this is our angle adjacent over the hypotenuse is going to be, is what cosine is equal to, and we have the hypotenuse, and we're searching for that adjacent line. So the way you would solve this, if you just do on your calculator, the cosine of 45, make sure you're in degree mode, cosine of 45 times 1800. So, and I think I got, I got 2,545.58, and that would be newtons per coulomb. And then back to kind of what, I forget who was saying it earlier, I'm sorry, but we'd have to multiply it by 2. And the only reason is we know that these two angles are the exact same. So theoretically, you could have a problem, right, where it's not exactly 45 degrees. And you have to kind of use some math and trig to figure out what the angles are, two angles are going to be. And you might have to use, you know, a different problem like this again to be able to add those two things together and then get an answer. But in this case, it was the exact same on either side. So I know that the amount of force that this is pushing with, the amount of force this is pushing with is exactly equal to this one. And that's only because it has the exact same amount of charge charge and the exact same angle. So therefore, the total amount of force that's pushing it this way is this times 2, right?
Real quick, you did cosine 45 times 1800 and got the 2545?
Yeah, I can double check it quick.
Because I think that the 2545, I thought that was the end number.
Maybe my work is bad.
You get like 1,272.79, and then you times that by 2, and
And
you
then you get this?
Yep.
I'm sorry about that. So what was that number again? This is
It's
gross.
1,272.792206.
Then you have to times that by 2, and then you get the answer. Sorry about that. Apparently, I copied. Don't do that. This is the reason. So you kind of, does that make sense a little bit? You could see maybe there, where if you had one where these two distances were different, or the amount of charge was different, it could cause that angle to be a little bit different. And how, I don't know if we had any problems, like, did we have any problems where they were different? I don't think so. I think they're all the same pretty much, right?
Yeah, I'm hoping that she keeps that on the test too. If they start being different distances and angles, it's going to be some serious math.
Exactly.
Well, I have a question. She said that for the short answer, there's going to be like 3 charges instead of like the 2 in this one.
Mm-hmm.
So is it going to be really similar? I guess I'm confused on how we're going to find or like do the a squared plus b squared thing with 3 charges.
Yeah, so I bet you it'd be similar. It'd probably be something like
In
maybe like
number 8,
this.
they have 3 charges.
You know, maybe these ones are all positive, this one's negative, or something like that. I'm just guessing. Then you'd have to guess, you know, what's gonna happen to the and what angle it's gonna come out. I can't see her making it. She did say it's gonna be 3. Let's just double check. I have my
Jeremiah
calculator.
is right. If you look at number 8, there are the 3 charges on there for week 7 for the homework.
Question 8, yeah.
Well, she kind of drew it like on the board how it was going to be for the short answer, and she had 3, and then yeah, just kind of how you drew it.
Yeah, it could be that or maybe a different variation, but it's still the same concepts. Like there's still triangles here, right? Like here's a triangle, right? Maybe you have, it ends up being something like this too. I know we had a problem like that where it ended up going down because of like I think that was part B in 9, where it was a positive and a negative. So it was pulling it toward this way, and this was pushing it, so it ended up going down. So it's just understanding what each charge is going to do to the particle, right? So in all of her examples that where the particle didn't indicate like a charge at all, it seemed to have a negative charge, kind of, right? Like in 9, it would work. It would make sense if it was like negatively charged, but she
Yeah,
didn't
you're right.
indicate it at all. Yeah, you think so? Okay.
Why don't we do this though? Why don't we give these some values? Because I feel like this is definitely
Sure.
going to be pretty much what's on the test.
Let's give it a shot. So, what do you want the values? Should we make them all the same, probably?
Yeah, I mean, just ones across the board basically is going to be.
1 nanocoulomb, and say this distance is, we'll say 2 centimeters. So is this distance. So what's gonna happen? Okay. Well, like we were talking about earlier, we're gonna need to find the hypotenuse to figure out, how much distance we have here, and then we're gonna need to plug it into our formula. So let's do that first. So we have 2 squared plus 2 squared is gonna equal r squared. So 4 plus 4, or 8. So it's the square root of 8. Oops. Which is, we'll say 2 square root 2. I don't know if that's easy. Maybe we'll do it in decimals. I'm
It
intrigued
would
right now.
be 2.83.
Cool.
But we need it in meters.
Let's do that. Well, I'm just gonna leave it there now, and then when we're plugging into the formula, we'll try and remember to convert it. So we'll indicate that it's centimeters for now. Okay. So now if we kind of scroll back up here, we have to use this equation, right? So I'm just gonna plop that down there. So then we want to figure out E. We'll have to do 9 times 10 to the 9th times our storage charge, which in this case is 1 nanocoulomb again. So we'll say 1 times 10 to the minus 9 over our distance, but now, like we were saying, we have to convert it. So 0.0283 meters squared. Let me grab my calculator really fast. Okay, I got it. Did anybody else plug this in? What'd you
I
get?
got- Yep, 318.02.
Does that sound good to everybody? Nine times 9 times 10 to the minus 9 divided by 0.0283 squared.
I didn't get that.
Oh, I forgot to square it.
Okay.
Thank you for checking. Yeah, I didn't square
Yeah.
it.
So what did you get, Mary? I got, say 50. Does that look good or no?
Wait. Oh,
Okay, yeah,
man.
that's what I got. I thought that was a
That's
little
what
big.
I got too.
Okay.
Okay. No, it's no worries. Everybody, that's why we're double checking, right? Always, I was gonna say too, on tests, we have a ton of time. Oh, any calculation you do it like 2 or 3 times, just to make sure, right? Because it's really easy to accidentally hit a button or put a parentheses in the wrong spot, or you know what I mean, right? Like it's,
Or forget a square.
yeah. No worries, Ethan.
It's always the smallest and easiest things that we tend to forget. So
Exactly. So and we have time and stuff, and so be careful, right? Always better to double check. Cool. So now we know kind of a force that it's coming out with on this side, right? So we can kind of replace this for now. Maybe I'll use a different color. So it's 11237.4. Oops. So now we're gonna have to figure out. It seems like it's gonna be 90 degrees again on this side. So that means this is gonna be 45 again. So we're looking for. So now hold on. I'll draw this out a little bit more clear, hopefully. We're gonna go straight through the line. This is gonna kind of keep going. We'll say that this side is gonna kind of keep going. So we know this angle here, or sorry, this angle here is gonna be 45 degrees. We know the force coming out on this side is this number. You see what I mean? Where I use this triangle, but it's really the same values as this triangle. And this is the one that we're solving. Like the side we're solving for is this, right? But now that I think about it, right? Do you guys think it's gonna go straight out to the right? That's kind of what we're figuring out, right? But
No, it's going to go down in some way because of the negative on the bottom.
exactly. So I don't know if it's exactly gonna travel down that path. I think it might go down this one, right? Because you have two equally pushing it this way, and then one. We can kind of test that theory, right? Is there a mathematical way to determine direction, or is it just mostly conceptual, Jeremiah?
Okay, I'm sitting here trying to think about it. So you could do basically that it's two problems. I think you could do the positives and then the negatives. Because with the two positives, it would be pushing it down. See that? I don't know though. Because you would have two angles. One's just pushing it at a flat, straight right, and the other one would be pushing it at a completely 45-degree angle down. They're the same force, so I'm pretty sure you would just cut that angle in half. Now, if they're different force, but they're at different lengths, see, that's what throws it off. I have no idea.
It's all the same length. It should be.
No, because one is 2.83 centimeters away and one is 2 centimeters away. So
Okay.
that one will have a larger force on it.
Let's just, I think in 8 what she did, right? Is she just wants to know what are the strengths and the directions of electric field at each position. Right? So let's just figure out how much effect each part of it has. And then we'll just kind of get that down, and then we'll figure out hopefully what angle, right? So right now we're working on this one, and it's pushing it toward 315. Sorry. So we're gonna do this one to be at a 315. That's where Jeremiah was talking about the unit circle, where it's kind of like this is 0 degrees, this is 90, this is 180, so this is 270. So if we're coming out at a 45 degree this way, that's gonna be 315 degrees. All right? So that's kind of what Jeremiah was talking about with the unit circle. So if we think about this like a unit circle, like a big old unit circle, you would say this is 315. Jesus, I'm sorry. Okay. So we'll call this one will be E1, E2, E3, right? So then we'll say E1, we can do, it's gonna equal cosine 45 degrees, right? And we have cosine is adjacent over hypotenuse. We have a hypotenuse. We're trying to figure out the adjacent. So it'll be x over 11237.5. So E1 will be, let me double check, cosine of 45 times 1. So I got 7,946.1, we'll say. Is that right? What do you guys think? Yeah. So
I got that.
yeah. Cool. So what direction is that, is E1 here, is pushing our particle down?
Would it just be down to the left?
It'd be kind of this one, right? Because it's kind of, it's pushing it out. So that's where I was kind of getting into the unit circle. So, I mean, you could say like down to the right or whatever, but I think the proper way to say it would be 315 degrees. So you would say actually towards 315 degrees. Does that make sense?
Do you know if we have that unit circle anywhere in our notes?
I don't think so.
I know, I don't think that we, I don't think,
What's up?
But like when our group asked her, like, oh, you guys learned this in like whatever math class in college, and all of us were like, we didn't take like any math classes in college. So I don't think like that she plans on all of us using a unit circle in general.
Okay.
okay.
Well, I think the concept isn't too tough. It's just the idea that, okay, you know a circle's 360 degrees total, right?
Mm-hmm.
And we always start on this point here on the right, and you go around counterclockwise.
Yep.
And so you just use that idea to kind of say, okay, this is 0 degrees, 90 degrees, 180, 270. So you can see how this is like a 90 degree angle, right? So if we
Mhm.
go from here to here, it's gonna be 90 degrees. This is like a flat line, so that's gonna be 180, right? And if you had a 3/4 turn, that'd be 270. So if you look at our thing, if we kind of look at this as a big unit circle, geez, I was on. You look at this as a big unit circle, right? And this is your X and Y. Maybe I'll use a different color. This is like a big unit circle around it. This direction here. So if this was 0, 90, 180, 270. This is about 45 degrees plus 270, so 270 plus 45 equals
So
315.
315. Okay.
Does that make sense?
Yep. Thank
So
you.
this, so this angle here is 315. So that's where we're getting that. I'm not sure if that's, if I'm sure you'd get some credit if you said, you know, down to the right. If you recognize what direction it was and maybe didn't say the exact angle. Hopefully she'd be a little lenient on that. If, yeah, not many people have taken trig or algebra or anything like that. So, okay. Well, let's think about the second one now. This one should be a little bit easier, right? It's just pushing it straight toward the right. There's no angles going on. And it's just pushing it with 1 nanocoulomb. And the distance is just going to be this 2 centimeters. So we can kind of plug in that stuff into our equation. So we'll say E equals, we still have to use that K, so the 9 times 10 to the 9. We still have 1 nanocoulomb. I'll write that out. 1 times 10 to the minus 9. And then we have 2 centimeters this time squared, which will be, so 0.02 squared. Because we have to convert to meters, right? So let's plug that in. So 9 times 10 to the 9 times minus 9. So I got, what do you guys think about that?
Yep, that's what I got too.
Cool. So then we can say E2 Does that make sense? Yeah, because it's just a shorter distance. Jeremiah, those numbers make sense?
Yeah, it's definitely going to have more of a pull on it the closer it is,
Okay.
or push on it, whatever.
So we'll just say to the right. And then we'll do the last one. I think we kind of already solved a lot of the math for this one, right? But it's just going to be backwards. So, in
So
this
we
case,
didn't have to do anything with cosine for that one? Just
no.
because it's straight? Okay.
Yeah. Yeah, it was just straight. It's just pushing it out that way. So we don't need to know. The reason we have to know, like, the cosine stuff is if we know what direction it's going in. So I'm kind of have a feeling, maybe I'm wrong about the cosine stuff on this one, because that's why I'm wondering about my values. Like, this number seems like a very high number compared to this one, right? When they have this same exact charge. So if we're not looking at exactly what direction it's going in as a whole, and we're just looking at each element, I think we don't really need to do the whole cosine thing. So I think that this number should just be the, you know, am I wrong there? Because the reason that we used the whole cosine stuff in number 9, problem 9, was because we knew what direction, by looking at it, it was going to be travel, like that by the end, after all the forces were affected, we knew where it was going to go, right? Where in 8, it was kind of hard to tell, and she didn't really ask us to even figure that out. She just asked us, like, what is each element going to do? And this element is going to push it at 315, like we said, but it's going to push it straight out the same way that this one did, right? So maybe we don't have to do the cosine for that. And that would make sense to me. Because when we use cosines, we're trying to find like this kind of thing. Like if all three of these were positive and we knew it was going out this way, we'd have to use that cosine stuff, right?
I think you might be right because like you said on 8, we didn't do anything with that. But we did say like where it was pointing.
Mm-hmm. So
So
maybe,
but we
yeah,
don't use
I think you're right. I think you're right. So if we have a problem like this and she doesn't ask, so in 9 she asked, what are the strength and position of electrical field at the position indicated by the dot? Where in 8, all she says is, what is the strength and directions of electric field at each position? So if it says each position, we'd have to do something like this, where if it was just overall, we'd have to do more with the cosine and stuff. So if she said it was going to be 3, I have an inclination to say that it's probably going to be like one of these types of problems where you have to find each one and the direction that each one is going to go.
Let's just all do it this way. So if we
Yeah.
can't mark it wrong.
By the way, you do have to do the cosine. The reason it doesn't change it for E2 is because cosine on the unit circle is 1. So cosine at 1 times the 22,500 would be 22,500. It would not change the value. Cosine 1, which is what the unit circle ends up being,
Mm-hmm.
is 1. So you don't change the value. So you don't have to do cosine for E2 because it's at that level.
But do you see what I'm saying about number 8? How we didn't have to use cosines at all? On week 7 problems?
I think I think you have to use it when there's more than one force acting upon the unit. Isn't number 8
So number 8,
basically one at a time?
yes. And that's kind of how I was doing this one. So when saw for E1, I used like the cosine, but what the cosine was doing was solving for this. But we just wanted to know how much force it's going to push this way with, because we're doing it kind of one at a time, right? Does that make sense?
Yes. And if E2 did not exist, I think you'd be able to get the exact angle and the exact force. But the
Yeah.
concept that E2 is at a different angle and a different force because of the different distance, you are going to end up with incredibly difficult math. I
Yes.
very much doubt she formulates it like this. I would guess that she's going to have E2 basically directly across from either E1 or E3, and that way the trigonometry will be very simple because it will be the same distance and the same angle.
Okay, so you're saying if we were trying to figure out, like kind of like we did in 9, where this particle is ultimately going to actually go, kind of.
Yeah, with this amount of variables, it's going to be crazy math. So I
Yeah.
don't think she's going to have us do this.
That's kind of what I was doing, where I figured we're not gonna be able to figure that out in this situation, so I was just gonna kind of show each one what its effect would be on the thing, which was kind of like what 8 was, right? 8 was just,
Absolutely.
yeah,
I know we haven't had anything like this, but when we were going over the short answer in class, she drew it like this.
I am praying that it's not actually like that because that is
Yeah.
some great because you're going to end up with some random angle and the force will be dictated mainly by E2, but not all the way. It would be insane. So let's pray that it doesn't.
yeah.
And then if it does, let's learn a different problem because I'm not doing that one.
Well, I mean, we're almost done. Let's just figure out the last one. I was gonna
Sure,
say,
absolutely. Because that is the way to do it. That is the perfect formation.
mm-hmm. You're right though. This is tricky. This was one I just, we made up, so we didn't know
Yeah,
if it
yeah.
was gonna work out. Yeah. But we know that this one's going to be also 2.83, right? So that means it's also going to have that same amount of force. So I can even just kind of take this and plop it right here. And it's going to have that same force, except now it's pushing out at 45 degrees. So we'll say 1,237.5 newtons per coulomb towards 45 degrees. So that'd be my answer. That'd be the best I could do for that one. If that's hopefully all she would want, right? Like I can tell you what each one's gonna do. I don't know what's gonna happen at the end.
That's a great way to put it. Absolutely.
Okay. So that kind of covers like a couple different ways that we could possibly have a question for that 32. You guys want to move on to 33? Yeah. So 33 says, how many potassium ions, positives, travel through the channel? Time, current, radius. What is the resistance? What is the power? So we were kind of talking about, so potassium ions, just think, I know everyone kind of gets caught up in this ion word. Just think, an ion is like a charged particle, either positive or negative. So, but usually it's a positive. So in our case, it's like if you see the word like some metal in an ion, think proton, right? So how many protons travel through the channel? Or electron, I mean. Wait. No, it'd have to be protons. But if you're given basically these values like a time, current, and a radius, and you have to find resistance, I think she'd probably also maybe give you a resistivity, like a rho, right? Remember we were talking about that? So if we're given, it could maybe be something to do with this one. So that's hard to tell. Does anybody think there's any like homework problems that are similar, asking similar questions to that? Okay, because now I'm outside of resistivity and resistance.
No, that's what makes this one so intimidating. Is she mentioned it one time in the notes. We never did any homework about it. The only thing that it talks about is the copper cords, the resistance for the cords by its area and length and everything, a little
Mhm.
bit. But as far as the batteries, I don't think she ever mentions it again.
Right, so
Jeremiah, do you know what page that's on?
Yes, 1 second here.
Yeah.
Oh, it's one of the hundreds. It's between 100 and 110.
Okay.
like by week 9 homework, kind of.
Yes, week 9 homework, and it's the like 4th page in that. Back. Sorry, the page numbers don't help when there's like 10 of them. But yeah, it's in week 9.
Yeah. Okay. All right. Thank you.
I think it maybe has to do something with this one, or I'm just thinking if we had a time. I can't see any time ones, you know. Maybe just knowing that like the whole idea of Q over T equals I, right? I think that's on our circle though. No, it's not. There's no time on the circle. And I don't really see it on. That'd be my guess though. It's just because if you're given, it says you're given time current, right? So you're given I, T, and maybe radians, right? You can kind of solve for the Q, the charge, and then you can maybe use some of these guys or some of our other equations that we went over to kind of get there. Like, because then you can know, if you know the key Q, right, you can find, let me think. I just want to see if there's a problem similar to that. We didn't have anything on the homework that was like similar to that, right? That one seems like a tough one. Maybe it'll be more obvious like when we get there, but there's definitely equations that we have that have time, current, and radius. It just, I don't know the context of the problem, right? Because it could be like, it also asks like what's power? So power could be, you know, work over time, or power could equal this Q times epsilon over time. So maybe you would need to know kind of a mixture of these two.
So basically, like for like 33, just kind of the wheel will be your best friend in this problem then, since it's asking all of the like the resistance, the power, time, and current, or
Yeah, if you can figure out
like
the
you can
resistor, you
manipulate.
figure out the power.
Yeah, you can manipulate the time over I equals, I think, was it V over time? But you could find that through that.
Exactly, yeah. Because I think
Yeah.
I also, I think I wrote that wrong. I meant to do that.
Or, yeah.
So using kind of these two, right? So if it's, because I think it says, yeah, what is the resistance? If you know power and current, you should be able to figure out resistance using the wheel, right? I think there was one of those in there with those two. So if we look at our R and we have power and resistance, oh, maybe not, right? Well, okay. It looks like, I mean, I'm sorry, we have a power and a current, so we can use this one, right? To find resistance. So yeah, I think it would be these two for that question. So hold on, jeez, I wrote a lot. So these two would be my guess. So knowing that power is Q times epsilon, remembering this is like, can't remember off the top of my head, to the minus 12, I think. Right? Somebody know that one? The permittivity constant?
Yep, you're good. It's to the
Yeah.
negative 12. Yep.
Cool. So that one, that would make the most sense to me, based off the question. It's kind of vague a little bit, and we didn't really have many examples, but if we know time and current and radius, well, this doesn't really do radius, does it?
Would we use the radius to find the resistivity? Because for B, we have to find the resistance. And she said she'd give us the resistivity.
So if we're given the resistivity, so there's a difference, that's right. So resistivity is that rho, it's like that squiggly P, it's this guy.
Yeah, that and length, she said she'll give us for B.
Okay, so then I'll toss this one in there too. So resistance. As might be one as well. Is there any other ones that might be fair play? I mean, I think we
I
got it
think there was
covered
those
here.
homeworks where we had to figure out chunks of wires resistance. I bet that is exactly what it is.
Like on problem 9 or number 2 on week 9,
Yes,
you think?
because in that case, she said it is the same material. She didn't give us the material.
Mm-hmm. They're all made the same, yeah. That's a similar one. I'm looking, but she did say, she said, in my notes at least I have, how many potassium ion positives travel through the channel, time, current, radius, and then B, what is the resistance, and C, what is the power? So I figured from these two, if you're given a time and a current, you can solve for Q, and then you have that same time and Q and epsilon, you'll be able to solve for power. And then if you have power and current, you could do, sorry, this one, right? Power over I squared to get your resistance. So maybe I'll add that one in. So that's just what I saw looking at it and what she saw. You see what I'm saying though? Like you might need kind of all three of them though to figure that out. There may be an easier way, but
How would you figure out how many though for the first part?
what do you mean? How
'Cause it
many
says like how
potassium
many
ions?
ions?
So that would have to do then. So um so once we figure out Q, right? What is Q's units? So Q's units. Coulombs, right?
Yeah.
So coulombs. So if we have a Q by solving for our current and our time, we can solve for Q. We're given the value in coulombs. We know that 1 coulomb is equal to, I think it's 6.84 times 10 to the 18. I wrote it down a couple times. Hold on, where is it? Wrote that down in the beginning.
Yep, it was the 6.24 times 10 to the 18th.
Dang, I'm pretty good, huh?
Yeah.
Just kidding. Times 10 to the 18th. And that's electrons, right? So how many ions would travel through the channel? If we're given a Q, we just times whatever our Q is by this, and that's how many electrons would travel
Okay,
through.
thank you.
Okay, by ion, she means electrons?
It could be protons too, right?
Yeah, okay.
It's the same value either way, right? From what I understand. In mine it says positives, but we know that maybe it's a trick question, right? Because positives don't move, right? Protons don't go anywhere. Then I have it's indicated as positives. So maybe it's a trick and she's trying to be like for you to recognize that, well, none would move, but this many electrons would move, right? Maybe that's the idea. Because yeah, we went over that, right? Like what makes something positive isn't necessarily like extra protons. It's more a lack of electrons. Like I don't know if we did, you probably learned about this in physics 1 but there's no such thing as cold. It's just like the absence of heat. You know what I'm talking about? So it's a similar idea with like electrons and stuff. Like there's no such thing as like protons moving into something. It's just like electrons leaving something, right?
Yeah, because heat is energy. So if you have no heat, you have no energy.
Exactly. So it's kind of a similar way to think about it, right?
Yeah, so we must be talking about electrons because that's the only thing that would be going through a channel.
Yep. It's kind of where I'm at. And if she does say indicate that it's like they're protons or they're positive, then she's trying to trick you, I think. And I mean, on the first test, if I remember right, there were a couple like kind of trick questions on there. So be careful maybe, right? Like I remember there was one where I got wrong because I like did all the math and circled the value without realizing that all the values were equal to each other and that all of them were right. I felt like that was kind of a trick question, but you got to be paying attention, right?
It's very sneaky.
Yeah. Okay, so that's kind of a lot of information for 33, I think. Hopefully that helps a little bit. I know it's getting late, so I kind of want to wrap it up pretty soon. I have another test that, well, I know a few of us do. I have a micro test like directly after this physics test, so it's gonna be a fun day tomorrow. 34. How to use a multimeter. I think we talked about that earlier, so let's see if I can find it. We said that resistance is like indicated by this symbol. You have to measure it in parallel with no power. And that's kind of the big thing with resistance for sure. No power. So if you wanted to draw that in a circuit, so you had a resistor, you'd have to hook up your ohm thing, kind of like something like that, right? Voltage is indicated by this symbol, and in parallel with power on, so kind of the same thing, right? So if you had a resistor, this is where you would want to hook up your leads on either side. And then current is measured in the A button, which stands for amps, and you have to do it in series, so that would be more like this, right? And then you'd also have to remember that you have to switch the leads over. But I think we've all had a decent amount of practice with multimeters, right? That should be kind of a gimme a little bit. If not, maybe you should let us play with them a little bit before the test, right? If we go in early, I'm not sure if she would or not. Maybe not. Does everybody feel good on that, or you want me to elaborate a little bit more on multimeters, or no?
Can you just say what the leads are supposed to be at, like do you know that?
What do you mean?
Like, you know how we have to change the leads for like current?
Mm-hmm.
What are they supposed to be like changed to?
So remember there was like kind of 3 spots to plug in, and there were 2 different spots.
Yeah, on the bottom.
Mm-hmm. So what she said on the notes was, let me see, I think I passed it, was that the only one you had to change the lead for is when you're measuring current.
That's correct. It's the one on the right, and it's just for current, and it's because volts and ohms are measured in parallel. So I've thought about that more. You do measure resistors in parallel. That makes sense because
Okay.
current is the only thing that you have to do the switch for.
Gotcha. So yeah, that'd be the only thing to know.
That makes sense.
Yeah. Thanks, Jeremiah. So anybody else have questions or no? Does that cover your question?
Yeah, that did. Thank you.
So maybe we can try and do 35. So draw a nice clean schematic of a circuit. So maybe she'd, give you a picture. You just have to know all the elements. So know that, batteries, the longer side here is going to be positive. This is negative. If she wants a nice clean resistor, you kind of have to make sure that one side is going out. I don't know if it matters which one's which. It probably does. Jeremiah, do you know if it matters, like whether you go up or down first?
No, not at all.
Doesn't? Okay. I just noticed too, like if it starts up, it's gonna end on the opposite and go like that. I bet she just wants to try to make them look halfway decent. Capacitors are like this, right? So we'll say resistor. Battery. What else do we got? We have kind of one of these guys. Be a switch.
You had an LED, which is the arrow always pointing towards the negative. So you can tell the direction by the diode because it literally is an arrow.
Here, hold on, I can't find where. Does it look kind of like, isn't it something like this? Or am I wrong about that?
That's part of it. That is what indicates the light. 1 second, let me draw real quick.
And then on
the
the other side of the line, you're just going to make it into a triangle.
There you go, Jeremiah allowed it. So wait, like this.
Here's it.
Nice. See, now my thing's freaking out. I don't know what I did. Whoops. Oh, there we go. Sorry about that. So this is what we decided? That's kind of what Jeremiah showed too, right? Yeah. So that's gonna
Yes,
be.
and the only other important part is the part that it's pointing to the negative as a line.
So, yeah, let me see yours. Gotcha. So like, let me restart this. Does that look better?
Absolutely, man.
Cool. So then we'll just indicate. So those arrows are pointing toward the negative. Is there any other components that we really need? We did capacitors, resistors, switches, batteries, LEDs.
No, I think that was it. I mean, other than maybe like a light bulb, but I think we all got that one.
Yeah. So then, yeah, just make sure you're following along, a good idea would be to always in a circuit, especially if it's just like a picture of a circuit or something, follow the positive to the negative, all right? And draw the junctions and kind of follow your finger along. Where's the, the current gonna flow, right? Um, yeah, I think that pretty much covers that. Anybody, any questions on that, on drawing schematics? Good. Those aren't too tough, right? I think any of these so far, I'm probably gonna go for, well, the first one's easy, right? Second one is kind of so-so. Third one maybe, and then the fourth one's easy, right? So for sure the 31 and 35 for me. 36. Capacitance for 3 capacitors is given. How do you get the most capacitance and the least? I was kind of confused on that one. I was maybe going to pass it over to Jeremiah to try and explain. How would you get the most and the least? Would it just be like parallel and series?
100%. This is by far the easiest question. Okay. She said the only way it's going to be hard is with the math. So I'm assuming what she's actually going to do is give us like 1 in nanofarads and then 1 in like millifarads or something. That's the only way she can make this difficult is by changing the units that it's in. So if you can get the units correct, to make it big, you put it in parallel. To make it small, you put it in series. That is like the answer to that question. The only thing you have to remember is that equation, and it's opposite of resistors. So in parallel, it gets big, in series, it gets small.
So yeah. Biggest put in parallel, smallest put in series. Remember, in parallel, you add them, and in series you have to use inverses to add. And that's why it would make sense, right? Like if you're just adding them all together, you're obviously going to get a bigger value than if you have to do the inverse thing, right?
Mm-hmm.
So yeah, that one is probably the main thing. Jeremy, I would agree with that. Is the only tricky part would be that. And good thing you mentioned that. That's a good point.
Because that's the only way to make it even mildly challenging at this point. That is the answer, like what's on the screen right now.
Okay.
Um,
All right, so 36 is kind of not too bad. So we got 3 like not too bad ones. Let's do 37. 3 resistors are given. Put them together and get 4 different total resistances. So how many ways can we put together 3 different circuit or resistors, right? I think she kind of talked about this. So the first one, you could have them all in series. That would give you 1 value. The next one, maybe you could have you could have 2 in parallel going to 1 in series. And then maybe you could have kind of like the other 2. Right, so if we put values to these, so this is 1, 2, 3, let's say, ohms. You'd have the 1 and 2 and the 3, and then maybe you could have the 1 and the 2 and 3, and then maybe you could have, I don't know, something like, I'm trying to think, would it be the same thing you did?
that's a good one. That's going to be a hard one. I was going to say it's definitely the most complex.
right? So that, yeah, so this would be 1, 2. So then you'd have to add those, and then you do parallels. So I think this, all 4 of these would give you different values, right?
Yep.
If you total resistance, cool. So that's kind of 3 examples, right? It's just setting them up, and you have to know that whole. The main important thing is knowing that for resistors, in series, you add parallel. I'll learn how to spell that word eventually. I'm only 25. In parallel, you do the inverses. And then for capacitors, it's the opposite. Right? So that's the kind of idea here. You'd think, in here you'd add them all. These ones we'd have to do the inverses, and then after you do that, add them. It'd be the same thing for this one, but just different values. And then this one's where it gets a little trickier. You'd have to add these two, and then whatever value you get for that. So it'd be like this. Right? And then this would be 2 still, and this would be 4 then. So you get a different value, right? So you have options there, for sure. Because you could have just did maybe, this again, but with 1 and 3 and maybe 2 or something. Even though I think maybe that would give you the same. I think that'd be different too. So that one's not too bad. 37. And 38 I know can be tricky for some people. That's the most recent one we went through with doing circuits and stuff. So I was thinking maybe I'll just I'll go through number 2 on lecture 11 just because that was kind of a little bit more simple of one. And we should be able to get through it a little bit quicker. Go through the ideas. Because all the ideas involved we've talked about already. It's that whole, knowing how to add together resistors and capacitors in series or in parallel. And you also have to remember that in series, current stays constant, and in parallel, the voltage stays constant. And so those are the kind of main pieces of information that we need to be able to figure these out. So this one was kind of simple. So then we had called this 40, 160. Oh, I did put it there. 48 and 400 and 100. So I'll call this R1, 2, 3, 4, 5. So okay. So the way to do this is the best way I think about it. You always know, so this is the positive side of the battery, and this is the way that we're going to want to follow the flow of the current, right? So this is going to come out of the battery, and it's going to hit this junction. Well, we want to know the total, because that's the first part of these questions, is calculate the single resistor value. So because the current splits here, that means, well, we must be in parallel. So we know these are resistors. So to add resistors in parallel, you do 1 over each value added together. So 1 over 40 plus 1 over 60. And if you add that, you should get, let's see. Plus 1 over, sorry. So you get 1 over 32. So then you got to do the inverse of that. Well, the inverse of 1 over 32 is just 32. So these two resistors combined become a total resistance of 32 ohms, right? So we can kind of redraw the circuit But I'm just gonna write now in the middle here, and we can redraw it later on. So after that, the current's gonna come out and meet back up at this junction. It's gonna come around, and it's gonna hit this 48. Well, that's in series, so it's not gonna affect the current at all, so let's not worry about it for right now, because this next part will affect the current. So let's kind of do the same idea that we did up here, down here. So 1 over 400 ohms plus 1 over 100 ohms gets you, what is that? 5 over 400, so I shouldn't do it in my head. 1 over 400 plus 1 over 100, 1 over 80. So the inverse of 1 over 80 is just 80. I'm gonna plop that here. And now I'm gonna redraw. So here's my battery, comes out, and instead of drawing this parallel, these two parallel resistors, I'm just gonna draw one. It's gonna be that new 32 ohm resistor. You know, for right now, I'm gonna use a different color for those, just so we can recognize that these aren't real resistors. They're values that we came up with, right? So this one's 48 ohms. And then we said that this one, I'll just finish my drawing quick, is 80. Cool. So now if we watch the flow current, it's all in series because it never splits, there's no junctions, and it just passes all right through. So we have resistors in series. That means we can just add them together. So if we do that, we get 32 plus 48, so that's 80 plus 80 equals 160, right? So that 160 is going to be our total resistance, or RT. Sometimes they write it as REQ if she's asking on a test, like find REQ. I would assume she'd probably put it into words, but it's a possibility that she says that. They're interchangeable. So now that we have a total resistance though, we can kind of go back through and figure out the values of all of them, right? So I'm just gonna go down here. Maybe I'll go like this to give myself some more room. I know it's smaller. Can you guys still see it?
Yep.
Yeah.
Looks good, man.
Okay. So we have a total of 5 resistors. So R1, R2, R3. Cool. So we can kind of start here. Our current is coming out this way, right? And we know, I'm sorry, I'm missing a crucial piece of information on this graph. This battery has 100 volts. We didn't need it up until now, because I want to figure out how much current is going to come through each of these, right? So I want to figure out the total current. So to figure out current total, I guess you would say, sorry, I total. You would get, because what is I, right? I equals voltage over resistance. That's that equation from the wheel. And it's probably the main one. Otherwise, I think Shannon taught it like this. They're the same thing, just kind of rearranged. But if we're trying to solve for I, it's useful to use it this way, right? So I'm going to take our total voltage from the battery, so 100 volts, and we're going to divide it by the total resistance that we just found. So 160, we'll say ohms. So then we know that our total current is 100 divided by 160. So yeah, 0.625, and this would be amps, right? Yeah. Cool. So now that's how much we know how much current is coming out of this battery. It's going to this battery and it's hitting this resistor. Except this resistor is a pretend resistor. We're going to need, so I'm going to use the knowledge that we know that in parallel voltage is constant, right? So that means both of these two resistors, R1 and R2, are going to have the same exact voltage. And the way I can figure out what voltages they're going to have is by using our new current and this resistance here. So resistance is going to equal, let me think, V over I, right? Because if you're trying to solve, yeah. So let's plug in our, voltage equals I times R. That's what we're using. Confused myself for a second. We're trying to solve for voltage, and we have these two, so all we have to do is times our 0.625 amps by our 32 ohms, our resistance. Now, if you were given values that were in milliamps or kilo ohms, you have to be sure to remember to convert for these equations to work, because for these it has to be in amps, these have to be in ohms. I mean, volts are always going to be volts, but sometimes they can be really small or really big, right? So you got to be able to kind of be on alert for that stuff. So if we do this, we do 0.625 times 32, we get a voltage of, maybe pick a new color, 20 volts. So because this resistor has 20 volts, and that is, these two added up, these two are both going to have 20 volts, right? So we can even throw that in. So for, this is R1 and R2, they're both going to have 20 volts. And then, now we can put in also their resistances. So R1 had 40 ohms, and R2 had 160. So now we can just use this same exact equation again to now solve for the current. Right, so I don't know if I used this color yet. So because we have a voltage and a resistance, we want to solve for this I, we just do the voltage divided by the resistance. So for this first one, it's going to be 20 divided by 40, which is just 0.5, right? So we'd get a current of 0.5 amps, right? Some people would write that as 500 milliamps, right? For R2 it's the same thing, but we're doing 20 divided by 160, and I get 0.125 amps, right? And so now we're done with those, so we can kind of just, this whole thing is done, right? No more worrying about that. Cool. So now we have to figure out, well, how much energy, right, or current is going to go through to R3, right? Well, pretty sure that looks like it's in series to me, and in series current stays constant, right? So these two values are going to make the current different, right? They have different resistances, and they're in parallel. Well, by the time once they come together, come back together at the end, they're gonna meet back up, right? And so I think they're gonna have that same current that we came up with earlier. Does that make sense? So it kind of splits apart in parallel, but then they come back together, and conservation of energy, right? It's neither created nor destroyed. It has to all go back somewhere, right? So they all meet back up. So I think for this R3, it's going to have that same 0.625 amps, right? And we know the resistance is 48. And so yeah, and then we have two pieces of information. And so we only need two to find the third. So if we're trying to find voltage, we use this guy, right? So we do 48 times 0.625. So you get a voltage of 30 volts. Sweet. So now we're done with this one. And we were back to another parallel, right? But we added that together here. It's this guy. And we know it's in series here, right? So it's going to have that same current going to this one. So we can figure out, do the same kind of process that we did up here, where we find the voltage, and then we know that voltage is constant in a parallel circuit, so that these two values are going to have the same voltage, right? So let's try and figure that out. If we are trying to solve for V, we have the current, because it's the full current coming off the battery, and we determined the total current earlier. So it's that 0.625 times our 80 ohms. So then I get a voltage of 50 volts. So we'll say 50 volts. So that means for both of these, they're both getting 50 volts. So we can plug that in our table here. So this one's R4, this one's R5. They're both getting 50. So 50 volts, 50 volts. We know they're two separate resistances. So for R4 it was 400 ohms. And for R5 it was 100. So we got two values for both of those. So I think we should be able to figure out the last ones. So we're trying to solve for current. So we're going to use this version. So I equals V divided by R. So we're going to take our 50 volts over our 400 ohms. So 50 divided by 400, I get 0.125 amps. And then for the next one, it's going to be that 50 over 100, so I think that's 0.5. Pretty sure. Right? I think that lines up with what I had on my sheet. So that would be our answers. We figured out voltage, current, and resistance for all of them. Does that make sense to everybody? Any questions?
Yes, it does. Thank you.
Yeah? Did that help?
Yeah.
Cool. So yeah, it gets more complicated than that. But I tried like breaking it down piece by piece so that you could understand the process and follow for a more complicated one, right?
She did say the one on the test is only going to have 4 resistors, though.
Oh, cool. So it won't be too bad then, hopefully. So yeah, for me, I know which ones I'm picking, right? Like I like 31, 34, 35, 36, and 37. That's probably what I'm gonna pick. Or 38, because I like these things too. Okay, I think that pretty much finishes up everything I had. So, does anybody have any questions, concerns, comments?
I just want to thank you for doing this again. This is definitely very helpful to do
Oh, no
before the
worries.
exam. So yeah, so thank you.
Mm-hmm.
Yeah, thank you.
Thank you so much. I appreciate you.
Well, I hope it helped a little bit. It's my studying too, you know, so, and I enjoy doing it.
Yeah, and thank you, Jeremiah, too,
Oh yeah,
as well, with your knowledge.
Yeah, definitely.
he's
You're
only
like the
of course.
making me feel
OP
halfway
in this.
confident.
No. Thank you, Brady. Absolutely, man. That definitely makes a difference.
But everybody feels good? How you think we're gonna do well tomorrow? Yeah? A little bit easier than the first one at least, right?
Right. I know. I hope that we're gonna end up doing good. You know, at least it's not optics.
At least it's not optics.